Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be continuing our study of finding roots of equations. We have been looking for solving a cubic polynomial equation generated by an equation of state, and we've been doing that by a lot of different techniques. This time we're going to actually start by looking at a different example to get started, and we'll come back to the equation of state. We are going to try successive substitution. In this case, what you're going to do is you're going to algebraically rearrange your function so that instead of being f of x set equal to 0, you're going to rearrange that function and algebraically solve it for one of the instances of x in your expression. So you're going to end up with something where x is equal to some new function of x. I called it g of x in this case. Now there are probably lots of different ways you can solve for that x, and every different form you create will be a little bit different in how it behaves. So they are not in practice equivalent expressions, although they should have the same value of x that satisfies it. One place where you've perhaps seen this already is in the thermodynamics textbook by Smith, Van Ness, and Abbott. They use this for solving cubic equations of state. And they take their generalized expression and they come up with these two equations shown on the screen. This first one here, they say is good and useful for finding vapor-like roots, values of z that are near 1. And the second one is useful for finding liquid-like roots or values that are close to 0. Both of them came from the same general equation. And in both cases, what you're going to do is you're going to guess a value of z, you're going to substitute it in here, and that will be your new guess for z. You'll take that answer, substitute it in over here, that'll get you a new guess, and just keep doing this process over and over again. When are you going to stop? Well, you're going to stop when you reach your relative error limit. So the relative error limit is going to be x minus f of x over x. And there's some disagreement about whether you should use the old x or the new x. Probably isn't going to make a huge amount of difference. If it's the new x, you want to say over f of x instead of over x. And that should be less than your tolerance. The programming logic is actually pretty straightforward. You're going to guess a value of x. You're going to figure out how's the most iterations I want to use, initialize my loop, and then start evaluating the function. Check the delta. If delta is within tolerance, then I'm done. If delta is not within tolerance, then I'm going to say x is equal to that function I just calculated. I'll increase my counter on my loop and go through the loop a second time. Let's look at an example, and this is a fairly mathematically trivial looking example. X over 3 minus e to the minus x squared equals 0. And we want to solve this for x, and so algebraically to me it looks like the easiest way you would do this is say x over 3 equals e to the minus x squared, multiply both sides by 3, and you end up with x equals 3 times e to the minus x squared. Okay, so let's solve that, and I'll pull up Excel. So I'm going to first figure out some x values. I need to do the graphing method, and my original function was x over 3 minus the exponential of minus x squared. And I don't know what x needs to be, so I'll just put in some values, 0.2, 0.4, and I'll copy that down a ways. And then my function is this x value divided by 3 minus the exponential of negative that x value squared, or times itself. Okay, and it looks like right in here I do have a change in sign, and so therefore I think that my answer is going to be near 1. Okay, and my form of the function that I'm working with is going to be this one where it says x equals 3 times e to the minus x squared. So successive substitution says I'm going to start with a guess, and I'm guessing 1, and then I'm going to use that function. So it's equal to 3 times, I don't want d3, I want 3 times the exponential of negative x squared. Okay. And since I'm using relative references in this, I can just copy this on down. And what you see is it goes nowhere. Right? It's just like bouncing back and forth. And if I continue this, it's not going to get any better. It's just going to keep bouncing back and forth. So that wasn't really a great plan. Let's go back to our algebra. I also have an x over here I could solve for. If I solve for that one, I end up with x equals the square root of the natural log of 3 over x. And if I do that in Excel, I will again start with my first guess of 1 and equals the square root of the natural log of 3 divided by that x value. And if I copy this down, you see that this one comes in and it's converging, not quickly, but it is converging to a particular answer. And so this one worked, whereas this one didn't. Okay. So sometimes if you have a successive substitution that you're trying and it doesn't work, you may do well to just simply look at your algebra again. So let's come back and look at our cubic equation of state again. So this is the Peng-Robinson for chlorine. And let's in particular look at this case 200 Kelvin and 1 bar, which we had both liquid and vapor solutions. And there are several ways you can do the algebra of a cubic polynomial. I've done 2 here, okay? And so one was solving for the z that was the az cubed. One was solving for the z that was cz. And if I do these 2 rearrangements, and I did these earlier, starting with a guess of 0, I did this, and this one is converging down to about 0.964, so this is my vapor-like root. And this one is converging to about 0.00245, and this is my liquid-like root. And notice this one converged fairly quickly, and this one was pretty slow, okay? But they did converge, and I am getting the similar pattern to what Smith, Van Ness, and Abbott had gotten. But it's very dependent on my starting guess. If I start with a guess of 1, well, that seems to actually help my vapor-like root get to the answer faster. But when I start with a guess of 1, it is a nightmare for the liquid-like root. It just gets totally lost and basically breaks Excel. Okay? So your starting guess is going to be very important, and the form of the algebra is going to be very important. That makes this a bit of a risky technique to use. Now, finally, I want you to write the code, and this time I want you to write your own code. This technique is substantially different than the other, so you're not going to really be able to directly just borrow and change what's inside the if statement, okay? You're still going to want to write a function for whatever your form of f of x is. And you're going to want to put in a starting guess for x and an error limit. So those parts you can borrow. But now then you want to create your own loop. Now I'm going to make 2 recommendations. Number 1, make sure you're limiting the number of times that you can possibly loop through the code. And number 2, before you run the program the first time, save your code. If by chance you have created an infinite loop, first thing to try is Control Break. You might also try Escape. If all else fails, Control Alt Delete. And that's why I said save your code. Because if you have to hit Control Alt Delete, I'm not promising that you're going to get your code back so that you can edit it. You may be starting from scratch. So this time you're on your own on writing the code. I think you'll be successful. At this time, this concludes this lesson. We're going to have a wrap-up lesson as our next video before we move on to numerical differentiation. Thank you very much for your time.